All right, so today we're going to be looking at inverse functions. And before we do that, we need to start off with the bigger picture and what is an inverse relation. Okay? And here's the definition. The ordered pair AB is in a relation if and only if BA is in the inverse relation. So let's take a look at that just a minute. So if this point, what it's saying here is that this point right here, this ordered pair, if this is part of a relation, then there's an inverse relation, and that point is on the inverse relation. So what does that mean? Well, let's take a look. What's the difference? How are these related? What happened? It's a simple switch of the x's and y's. So if AB is on the relation, then BA is on its inverse. You just switch the x and the y role, and that's now you're on the inverse relation. And that's the key to everything. So the inverse, I'm going to talk about the horizontal line test. Let's do the horizontal line test. I'll illustrate here with an example. The horizontal line test is used to determine if the inverse of a relation, but if the graph of the inverse of a relation is a function. That's what we're doing with the horizontal line test. So just like the vertical line test, the vertical line test was a test that if I look at the graph of a relation, and I can draw any vertical line anywhere I want, and if it hits that graph more than once, then the graph is not a function. If it can only hit the graph one point, no matter where I draw the vertical line, then that graph would be a function. So take a look at the same graph. If I have a graph, here is a parabola. This is y equals, or f of x equals x squared in some fashion. Let's do -3, whatever. But we can see that it will pass the vertical line test, which is why it's a function. The horizontal line test says this. Well, what about the inverse of this? Because functions are relations. And there is a point right here. We can call it, this is for the sake of argument, we'll call this point, 2, 2. I don't know, it's not, but just to say for the sake of argument. Bad choice. So 2, 3. Then the inverse of this, the point 3, 2 must be on it. That's what it says. Because every function is a relation. So if I have a point on a relation, then this point is on its inverse. So this point is on a function, which is a relation. So there must be an inverse to this relation, this function. And that point has a point on there called 3, 2. That's the definition. What we want to do is, can I then determine, is that inverse that I haven't looked at yet, is that inverse also going to be a function? Well, that's what the horizontal line test does. It's the same argument for the horizontal line test as it was for the vertical. If I can draw any horizontal line through this graph and it hits it more than once, then the inverse is not a function. If a horizontal line through the graph of a relation hits it 2 or more times, then the inverse of that relation is not a function. If it hits it once, then it would be. If you can only hit it one time, then it is. More than once, then it's not. So this one clearly is not. The inverse of an x squared is not going to have an inverse function. Does it have an inverse relation? Yes. Every relation, whether it's a function or not, has an inverse relation. But that doesn't make it a function. Okay? Here's an example of a graph that will. There's a bunch of examples. Here's the simple one. We'll just do the square root. So if I draw the square root graph, you can see clearly that this is a function. And it will also have, see, horizontal line test, it will also have an inverse function. So we can see that that's indeed the case. Here's a definition of an inverse function. If f, which is a function, is a one-to-one function, I will explore that definition in just a moment, with some domain that they call D, and a range we will call R, then the inverse function of f, and they designate it this way. Whatever the function name is, it's that function name with a -1, like up in the exponent. Okay, but because this is a function name, it's not an exponent. It's just a inverse designation. Because this is a function, it's not a number or anything. Then this is a function with domain R and range D. Now, there's a lot in there. Let's break it down. So first off, we talked about this thing called a function. So we have a function. I have already told you that we have a function. So it's more than a relation. It's an actual function. Okay? Which means it passes the vertical line test. We know this. If this function is one-to-one, well, what does that mean? What does one-to-one mean? And that's the key to this one. So one-to-one means, if you remember the definition of a function, it says for each element in the domain, so basically for every input, there is exactly one output, correct? Exactly one output. Well, one-to-one takes it one step further. One-to-one means for that word. For each input, there is exactly one output. That's the function part, right? And for each output, there is exactly one input. So what that means is this. You see this graph right here? It's a function, so for every input, I'm only going to get one output. That's the vertical line test says that. But the second half of this is, it says for every output, it only come from the same input. So in other words, here's a point right here with this x. Here's the exact same output with a different x. You see that? So this is not one-to-one. Okay, that's what it means. It's not one-to-one. Now, here's another way to look at one-to-one too. The function is called strictly increasing or decreasing. Okay, so you can look at it that way too. So what does one-to-one mean? That means a function is only going up all the time, or it's only going down all the time. There is no turning. There is no up and down. See, this one has, I go down and then I go up. This is not strictly increasing. This one is strictly increasing. See how the graph is only going in an upward fashion, correct? So this is strictly increasing. This graph is one-to-one, so it will have an inverse function. This graph is not one-to-one, so it will not have an inverse function. So this is another way to look at the same thing. From a graph, if it passes the horizontal line test, its inverse will be a function. Okay? So that's what all that means right there. We can also look at it in symbol form, this definition. And here it is. I'm going to give it to you. So F inverse of B is A if and only if F of A equals B. Now, a lot of symbols there. What am I really saying there? We want to break it down. If you look closely at it, let's see if we can remember some notation. Look at this right here, and I'll move my hand in just a minute. This says I have a function, and if I plug in the value A into that function, I'm going to get the answer B. So if I graph this information on a graph, aren't I just graphing that point? Right? This is the number I plugged in. That's the input. That's the A. And that's the answer I got after I plugged it in. That's the B. That's all that's saying. So that means if and only if means if that's true, then that's true. And what is this one saying? That if I plug the B into the inverse function, I'm going to get the answer A, which is that part. So it's really a symbol notation of this up here. If you plug in A, you'll get B into a function. And then if and only if, switch the X and the Y's role, you get the other one. If you missed it here, I said the same thing. I have a function whose domain is D and the range is R. What happens to the inverse function? The domain became the R. You see that? And the domain became the domain here became the range here. In other words, the output and the input switched roles. In this function, the domain D became the range D in this function because the X and the Y's switched roles. This is the nature of an inverse function. This is what's going on. Okay? Graphically, let's look and see what happens. How does all this play out? So I'm going to use an example to help illustrate this for a graphically. So I usually use a visual like so. Okay, and I just draw a simple graph that's over here. And I'm going to draw this one like that. I'm just going to call this f of x. I'm not going to actually try and give an equation for it. And on this, I know somewhere on here, all these points, we can label this as a generic point A, B. So all these points on here would be called AB. Okay? Well, if AB is on this graph, then by definition, and notice this graph, by the way, is always increasing, correct? Always increasing. So I know that it will pass the horizontal line test, yes? That means the inverse of this will also be a function. Okay? But if I look at this, what's going on here? Well, if this point is on this curve, then if I switch the roles of A and B, then I know that point BA is on the other curve. Okay? And so I can use a table. If I can find the table of this one, I can just flip all the X's and Y's, and I can graph the inverse one. And that would be a technique I would use. So if we look at this closely, at this point here, you see that A would be negative and B is positive. So it means B is positive and A is negative. This point is the point BA. And then it has to be on the inverse function. And if I drew this right, okay, then it'll work out. So I got to see if I can figure out and draw this. So it's going to come out like so. And it's going to curve like this. And then it's going to go like that. So it's going to do something like that. Now, that's kind of interesting, isn't it? This, because this is strictly increasing, and it passed the horizontal line test, I can see the inverse of this will be a function. So to designate an inverse function of f, I use the inverse like so. So this is f inverse. Well, here's something unique. It's kind of hard. I did a freehand drawing, so I might be slightly off. But the neat thing about this is this. If you look closely, it kind of looks like a mirror image almost, doesn't it? In fact, the mirror image is right along the line y equals x. And why would that be? It's not a coincidence. Take a look. This would be an x. This would be a y. This, over here, what happened? If this is x, then the x here is the y here, isn't it? Right? This y value became the x here, didn't it? This x value became the y value here. So literally, x and y were equal in that sense. That's kind of where that comes from. So inverses are all reflections. Inverses are reflections. Inverses, whether they're functions or not, is irrelevant. Are reflections across the line y equals x every single time. And you'll see this pop up again in just a moment. But that's how inverses and things go. So what I can do is if I can make a table for f and graph f, then I can switch the x and the y roles, and then I will have a table for the inverse function. And I can graph that one. Even if I can't find the equation, I can still draw a picture of it because I know that this graph and this graph are reflections across the line y equals x. How do I find the inverse relation algebraically? How do I find it algebraically? The reason why I say finding the inverse relation is because this technique will work for all, and you don't know, you may not know right off the bat if you're going to have an inverse function or not. This technique always works, and we're just going to use the definition. What is the relationship between a function and its inverse? We just switched the roles of the x's and the y's, correct? So guess what step one is? Switch the x and the y. At this point, you now have an equation that represents the inverse relation. There it is. Once you switch the x and the y, you have created an equation, a for the inverse relation. That doesn't mean it's a function. You just have the relation. Okay? That's what it means. Now, the next part of this is to basically go through this, and we're going to solve for y. The next step you want to do is solve for y. If you can't, then the inverse is not a function. Use inverse function notation if it is a function. Note, you might need to include restricted domain. I'll talk about that in just a moment. Okay? I'll show you an example of what I mean and why you got to put a restricted domain. Okay? We're going to start off as soon as you are ready. Here's an example. I want to use f of x equals the square root of x. We already know that that is a function. It's one of our parent functions. We know it's a function. We already described it on the other side, that this is also going to have an inverse function. We know what this graph looks like. Okay? So we're going to explore this one here and show you why you might need to include a restricted domain. So first off, everybody understands that this is just another name for y. So then the rule says you switch x and y. So that means I'm now going to have x equals the square root of y. This is the inverse relation right here. Solve for y. That means I have to undo the square root. So it means I have to square both sides. And so y equals x squared. And if you just left that, okay, you'd be incorrect. Let's explore this graphically. So real quickly, this graph of the square root graph is this one right here. So in the table, so here's x and here's f of x. I got 0, 1, 4, 9. I got 0, 1, 2, 3. Yes? So then the next thing is, all right, well, what's its inverse equation going to look like? All I have to do is flip the x and y table. So in other words, 0, 0, 1, 1, 2, 4, 3, 9. This is a graph of the inverse functions. This is the table for that. If I graph that, I'm going to use a dotted line so you can see it. I get that right there. Notice, this would be f of x. This would be the inverse of x. And notice, see how it's a reflection on the diagonal line? Okay, but now, what is this? This, if I graph this, is the parabola, x squared. But the dotted line is only this piece, correct? Whereas this, which is supposed to be that, has two branches, two sides, doesn't it? That's the restriction. So that's where that domain and range thing came from. The domain of this becomes the range down here, and the range up here becomes the domain down here. So this domain is all the x's greater than or equal to 0, and the range is all the y's greater than or equal to 0. So when I flip those around down here, I have to include the restricted domain. This range becomes my domain down here. It's not x squared. I have to eliminate this side. By doing so, it's still a domain. So this y switches to x. Remember, the x and the y switched, right? So then down here, I have to put x is greater than or equal to 0. That then can be written as f inverse is x squared when x is greater than or equal to 0. This is what I was talking about. This is this dotted line right here. Okay? This is why all three parts are important to understand what you're doing so that you don't make little mistakes like that. Okay? One more thing. Verify if two functions are inverses. So I have two functions. F of x and g of x are functions. They will be inverses of each other if and only if f of g of x equals g of f of x and has to equal x. Well, where does x, why x? Where does that come from? Y equals x. Okay. Another reason is this. When we do composition, okay, it's and they're inverse functions. So remember the little thing, the little factory we had, right? So I drop a number into here, the G acts on it for this one. It comes out over here, and then drops into the new factory for F. And it comes out as a new answer. Okay? So what does the inverse do? The inverse undoes that. G of f of x then takes that answer. If I take that answer I got here, undo the f, then take that answer and undo it with g, I should get back to the number I started with. That's what it's saying. Okay? So the inverses, if they're inverses, one is going to undo the other. That's what it's boiled down to. If I add by 5 and then subtract 5, I've undone. The operation was add and the other one was subtract. They were inverse operations. This is an operation on x, and f is the undoer of it. That's what an inverse does. It just undoes it. Same thing here. So if they are both inverses of each other, then both directions have to be x. So if you use this technique to verify that two functions are inverses, you have to show this one and this one are equal to x. Just because one does not mean the other one has to. It could have been a fluke, okay? So you have to actually show both of these compositions and show that they are both x. And then you can verify and conclude that f and g are indeed inverse functions of each other. So this is how you would do verification of two functions if they're inverses. On a test, that's what I want. I don't want you to take one function and find its inverse and show us the other one. I don't want that technique. I want this technique. To verify two functions are inverses, I want you to go through the composition technique. Okay? So we're going to do some more examples off the video.